Okay, here we are once again at the Physics 105B video lecture. Physics 105B video lecture 3. And we want to pick up where we left off, which was we had an example for the variational calculus. So I'm going to keep working with that example a bit. Could very well be that we talked about the catenary last semester in 105A, but let's make this reasonably self-contained. So first, just as our topic, we're working on the variational calculus, and the example is the catenary. Well, we have the problem of finding a function y of x that minimizes, maximizes, generally speaking, gives us an extremal value of this b here. And this thing was the time it takes time it takes for a b to descend a curve. That's what I was looking for. B to descend a curve, or distance between 2 points in the plane, etc. Right now, this is just a simple version of it. We did have so now I'm going to introduce some nomenclature where the variation of phi equaling 0, and this symbol represents everything that we did in our construction. So this implies that d dx df dy prime f dy equals 0, the Euler-Lagrange equation. And I'll tell you now, this thing is going to become as familiar to you as Newton's law. Okay, it's that fundamental. In fact, when we get to physics, this will be Newton's law, among other things. Okay, so yeah, so this is something we're going to have to learn. So this represents the minimization of this object here. Good. So the example we had was the shortest curve connecting 2 points in the plane. And the next example was u equals integral gy dm, which we decided was integral g y lambda dl, or potential energy is equal to, I can pull out the g and the lambda. Remember, the lambda was just a linear mass distribution, linear mass density, g lambda, and then we had the integral of y, 1 plus y prime squared dx. So this example, and then we had this as a homework, show that the minimum of u occurs for the function that is the catenary. So I was claiming that there's a principle here that the potential energy is minimized. Well, I just pulled that out of a hat. But if you show that the curve that minimizes potential energy is the catenary, which is actually the natural shape that chain takes, then you could very well start to believe that principle. So this was for, this example was the catenary. And we did this last semester, but I'm going to set it up and just have us do it again. It's a nice quadrature, and then you'll be able to do them both side by side. And make a good problem. So, this is also homework. And what I'll do is I'll set the whole thing up the way we did in the past. Now, there's our catenary. What we do is we go into a coordinate system here, x and y. And we start here at the origin, and we have our cable, chain, rope, what have you, going up to this point here, and then we have a tension there. We can imagine just clipping away the entire left half of that thing, and then if we were to clip this part away, we would have to hold it exactly the way it was being held. And so here we have a force, I'm going to call it, and we have an angle theta. So this construction that we did last semester, I'm thinking, but we'll do it right now again. This construction is just Newton's law. So we have net force equals 0, because this is a static problem. And so in the x direction, we say minus tension plus F cosine of theta equals 0. And in the y direction, we say minus mg plus F sine theta is equal to 0. And if we eliminate that force, we're just left with a tangent theta. So we have tangent theta, which is sine theta over cosine theta here, is going to be equal to mg over t. So far so good. Now what we can do is we can take the G and the T out here and ask what is that mass going to be. And that mass is going to be the integral of lambda dl again, as we just set up there. We're going to have G lambda over t, and the dl is simply going to be integral root 1 plus y prime squared dx. I have to put a little prime here on the x because we're going from 0 to x up the upper bound. Here, it needs more room. This no, we'll get rid of it. Okay, now going back to our picture and this expression here, we see that the tangent of theta is just the derivative of this function y of x that we're looking for. Okay? So this curve is a function y of x, so what we really have here is dy over dx is equal to g lambda over t. By the way, the fact that this tension is constant is something you might want to think about, because I'd assume that it's constant. You might want to think of an argument for why we know it's constant. So yeah, is everything constant pulled out here, and then we have this integral from 0 to x root 1 plus y prime squared dx, but x is an integration variable, and the upper boundary there is the variable. So yeah, there we have it. So what are we going to do there? Derivative, integral. So the next step is d squared y dx squared is equal to g lambda over t. And then remember, the derivative of this expression is the integrand evaluated at the upper boundary. So then we just have root 1 plus dy dx squared. So there's your problem. And what we're going to say is, so homework, you're going to let z equal dy dx. That's your first step to turn this into a differential equation you can solve. And integrate, by which I mean just solve the differential equation to eventually find y of x or x of y, whichever you prefer, and then y of x, I think, is what we want. And then you can compare this to the one we get through the variational principle, and if they're both the same, that's a hyperbolic cosine, then we'll be pretty happy. So then you see the utility of the variational principle and the variational calculus. Okay, so we have a number of more things to do with the variational calculus before we're willing to dive into Lagrangian mechanics. Let me just ponder this thing up here for a moment. Yeah, that's fine. Good. So yeah, that's a homework problem as well. Integrate this. Possibly we did this last semester, but you put it side by side with the variational version, and you've really got something. Okay, now we have a couple of more things to do. Very important is that this variational calculus that we had, so I'll go ahead right next. We have variation of f of y prime x dx equals 0 implies the Euler-Lagrange equation. Here's an example of a more compact notation for the whole thing. You'll see this, this kind of thing you'll see in the literature. dx df y prime df dy equals 0. Remember, we solved this for a very simple case, and you're going to solve it for a couple more cases. That reminds me, we have the surface of rotation as well, so surface of revolution. So these two problems, perfect. Now, what we have to do next is extend the formalism to functions with many different y's. So y sub 1 to y sub n. Because when we do physics, in terms of physics, this would be 1 degree of freedom. That's not enough. We need n degrees of freedom. We're doing multivariable. Okay. So next, so now extend to the variation of f of y sub 1 to y sub n, y sub 1 prime to y sub n prime, and x dx. So now we want to do the variation of something like this, and I'll just write y sub k is equal to d. Well, it's not partial, actually. So y sub k is equal to dy sub k dx, etc. So yeah, we did it for one variable. That was pretty intense, actually fantastic calculation. Hope everybody tries it and enjoys it. But it turns out that to extend the concept to n variables is not difficult at all. We've already done the essential work. I'm just going to have to formulate this carefully and declare victory as my proof. Okay, so I'll show you how that goes. The problem, of course, is that we have functions of many variables here, f, and what is our solution? We need y sub 1 to y sub n. So we're going to end up with a system of differential equations. If we had one differential equation, we're going to end up with some kind of system that can be solved to give us the entire answer. So for the many variable case, almost just cut to the chase, okay. The case of many unknown functions, y sub 1 of x to y sub n of x. And all I have to do is do this construction here, and I'll write the whole thing down and explain it to you. What we end up with is the following. Phi of epsilon 1 to epsilon n is equal to the integral, I'm going to write x sub 1, x sub 2, maybe I'll write a and b this time. 1 and 2. F of y sub 1 tilde y sub 1 prime tilde y sub n, I think tilde on top, x dx. So this is the same situation we had before, but many different variables. I'll give concrete examples of it, after we get the formalism out. And with y sub I tilde is equal to y of x plus epsilon sub I g sub I of x. Remember, this was just a real parameter. This was the function that vanishes at the end point. So your picture is still the same. You've got your point 1 and 2, you've got your curve, and you have your perturbed curve, and when when epsilon is equal to 0, this blue one turns into the black one here. G sub I of x1, G sub I of x2 is equal to 0. I'm literally writing down what we had before. With more of these variables in here. Now, remember, we're looking for, so let y of x, and by writing as a vector, I'm writing all n of them, I equal 1 to n, be the function that minimizes phi. Okay. And by construction, that phi of epsilon equals 0 is minimal by construction, just as it was last time, and d phi is a partial d epsilon I evaluated at epsilon equals 0. You've got that minimum there. That's the, by the way, that's the multivariable criterion for a critical point. All of the individual derivatives vanish at that point. And because of that, we've already done the calculation. The calculation just picks off, you know, y sub 1, y sub 1 tilde, y sub 2, y sub 2 tilde, y sub I, y sub I prime. Sorry, not tilde, prime. So it picks off y sub I prime, because that's those are the ones that are labeled with that epsilon there. Same calculation as last time, and I can write down d dx df partial y sub I prime minus partial f partial y sub I equals 0, I equals 1 to n. How great is that? The first time we did the calculation is all we actually had to do. Now we have a system of n differential equations that we have to solve in order to solve our problem, minimizing this thing. The immediate application is instead of a point, instead of a curve in a plane, if you have a curve in space, or you could have a curve on the surface of a sphere, you could have a curve on the surface of a cylinder. Okay, you want to minimize and you want to find out what that curve is, then you have two instead of one variables here to solve two differential equations. They're coupled and you solve them, done. Okay, so yes, the case of many unknown variables, many unknown functions, and it's the same construction, the same calculation. But what's very important, and this will come back in Hamiltonian mechanics, way downstream, it's very important, it's crucial that these were all independent, okay? Because I was able to take these derivatives independently. The independence was by construction right here, an epsilon and a g sub I on each one. And that means all the variables in this function have to be independent of each other. Otherwise, the whole thing just falls apart. And I'll actually give an example of that way in the future where that comes into play. Okay, good. So again, this is the equation I said you guys were going to memorize. And all n of them have the same form, so there's not much more to memorize, is there? Okay, so that's looking good. Let's check our time now. Okay, perfect. So I'm still doing formalism, and I have to prove one more theorem in this whole business, and then we'll be ready to transfer these results to physics. Maybe assign one more problem in some kind of geometry. Okay. But yeah, we need one more corollary of this entire formalism. And yeah, let's erase this here. So these are the Euler-Lagrange equations of the variational calculus. Even though there's no Lagrangian in sight, but there will be soon. So yeah, let's go ahead and write this down. Euler-Lagrange equations. So the next thing we're going to do is something that's referred to as Euler's second form. Well, this is the simple version of Euler's second form, the one we're looking at. And that is the following. So we're going to look at this expression here. We're now, by the way, we're dealing with what we have up here. Okay, we're dealing with this whole scenario on the board. And we consider the sum of partial f partial y prime times y prime minus the original function f. Okay. Where f equals f of y sub 1 to y sub n. But f is not explicitly a function of x. So when I'm writing this here, not explicitly a function of, it means that the explicit x in the expression there is not present. Okay, so there's no explicit x. We've seen cases where it exists and where it's there and where it's not there. That's what I mean. It'll go y sub 1 to y sub n, that's it. Okay. And then we're going to take then differentiate. Okay, so we're going to differentiate this whole expression here. By the way, I equals 1 to n, I and I. So d differentiate d x sub k of this whole thing here. d dx sub k. And what we're going to get is sum over d. Oh, no sub k here at all, sorry. This is that variable. Just differentiate with respect to x. So then we're going to have sum over I, d dx, df, I'm doing the product rule right here, dy sub I prime times y sub I prime plus df dy sub I prime times y sub I double prime. Okay, so that's differentiating this. Now I'm going to subtract off, differentiate this f right here, minus sum over df dy sub I, y sub I prime, that's chain rule, minus sum over df dy sub I prime, y sub I double prime. Okay. So that was the chain rule. You know, I made a mistake here, but I can catch it. What I'm looking at is f y sub 1 to y sub I prime, y sub n prime, but no x. Okay, that's what I just took these chain rule of. Okay, so I've taken that derivative of this expression that we're studying here, and let's see, we're going to get some cancellations. This y double prime term is actually under a sum. Let's go ahead and put it here explicitly just so we don't lose it. This one here, and then cancels against this one here. So this goes away against that, and we're left with something pretty interesting. You see they both have a common y sub I prime, and we're left with sum over d dx partial f partial y sub I prime minus right here partial f partial y sub I. I'll put a bracket around here, y sub I prime, I equals 1 to n. So we've differentiated this, we've obtained this expression, and look, inside the square bracket is the Euler-Lagrange equation, and these vanish. These all vanish. That means this thing is 0 as well. We have a conserved quantity, we could say. We have a first integral of a first integral. This is going to be a conserved quantity when we're doing physics. And so this thing is pretty important here. It's constant. So since its derivative vanished, this is constant. So we have sum over partial f partial y sub prime, y sub prime minus f of all of its variables, but not x, is equal to a constant. Okay. Very important expression. Even in the one variable case, by the way, this is true in the one variable case, because if you have the function here, right, it's in our variation principle, if this function is not explicitly a function of x, then you immediately have a first integral for it. So in the case of a one variable problem, you wouldn't want to solve the Euler-Lagrange equation because that's a second order differential equation, so you would use the Euler's second form right here. You know, one short way to write this is y prime x vectors. No x there. Okay, so this very important expression, and we'll do a problem or two with this, and then when we get ready to do Lagrangian mechanics, we're actually going to inherit this entire formalism and change the names of all the variables. Okay, and it'll turn into physics right before our eyes. Okay, but right as for what we have now, it's a great branch of mathematics. They're just very interesting problems we can solve. So maybe we'll do one or two more. The ones I've already formulated for us are pretty beautiful. Let's see how we're doing on time right here. 31. Okay, yeah, we have a few more minutes. I'm trying not to run these lectures out to the full 50 minutes because the idea is, first of all, there's no back and forth here. And the idea is if you write them down and leave a lot of room, you can actually just work on the lecture notes. There's a ton to learn here if you just space it out and try to understand every step that's being done. Now's your chance to do that. Okay, so we have this. And I think I will give us one more problem. Some nice minimization. And we'll call this a homework problem as well, and I'll set it up. Let's say the shortest curve connecting two points on the surface of a cylinder. This is one that's actually really great because if you're clever about it, you can just solve it by pure thought alone. But we're going to go through the formalism. Making 2 points on the surface of a cylinder. Yeah, so what about the surface of a cylinder? Say we had X, Y, and Z, and there's our cylinder. We need some coordinates for that thing. I would say cylindrical coordinates that we have some familiarity with. You would have cylindrical coordinates, so let's go ahead and write that down first. But the radius is constant, okay? Radius of the cylinder, we could call it A. So then we would have X equals A cos phi, Y equals A sine phi, and then Z is equal to Z. The thing is, we want a length element. We want a length element dl. And we can use the Pythagorean theorem here, because we know that these coordinates were orthogonal and normalized when we did the cylindrical coordinates. Okay? So we're not actually going to have to use the phi hat and so forth, but it's in the background there. So what is the length element going to be? It will be, it's going to turn into two. This may drop into one variable after all. Length element, we will have actually, let's let you guys find that. That's not bad at all. I just gave the hint, of course. There will be two variables, not three, because we're on the surface of the cylinder. So go ahead and find the length element in cylindrical coordinates, kind of thing you can look up anyway. You don't want to give everything away. So you find the length element in cylindrical coordinates, and then your L is equal to integral dl, okay, the way we did before, right? In the plane we had L was integral dl root 1 plus y prime squared, okay? Now you're going to have, the parametrization can even be the angle phi. You're going to have a length element there, and then your dl equals 0 will give you two Euler-Lagrange equations. Two Euler-Lagrange equations. If you can say to yourself, well, I want z to be a function of phi, if that's general enough, you would go down to one Euler-Lagrange equation. So you can solve this either with 2 or 1, but at least formulate it first with 2 in order to make use of the two variable formalism. Okay. There's an idea. So yeah, length element, then the minimization of that here. And good. I think that's where we'll leave. That's where we'll leave off for today. Anything else to say? We could do the shortest curve in space. So that would be a straight line again. You'd have parametrization for a straight line. The shortest curve connecting 2 points in a cylinder is very interesting. So you want to formally show what it is. You know what? I can't resist telling you another way to understand it. If you have those 2 points on the cylinder, right, and you slit the cylinder open like a piece of paper and lay it out on a table, what's the shortest curve going to be connecting those 2 points? Okay. It's going to be a straight line, and a straight line wrapped up in an angle on a cylinder is a helix. Okay. But you want to prove that also with the formalism. Okay, good. I'm going to check the time now, but I think this is a perfect place to stop. So we have the variational calculus formalism now, and what we're going to do next time is bring it back to physics, Lagrangian mechanics. It'll be the same Euler-Lagrange equations for a certain object here, and all of these expressions and differential equations will just translate into the physics of it. Okay. It's a great thing. Okay, see you guys next time.